Okay, we'll get started. In this video, we're going to be going through 3C, which is weight and mass. So the first idea is that weight and mass are two different but related ideas. So weight, mass, they're not the same thing, but they are related. So we're going to actually first look at this table is going to kind of help us understand some of the key differences between the two. So mass, the definition of mass is that's the amount of matter present in an object. So I'll actually draw it out a little bit down here. So if you have an object, that's just the amount of stuff that's in that object. So again, that's mass. Technically how many atoms of some kind are in an object. Weight is a little bit different. Weight is a measure of how much that object is being pulled down by the force of gravity. So again, gravity is a force, and weight's going to measure how much that object's being pulled down. So that's kind of the difference. Mass, the amount of stuff. Weight, how much that stuff is actually being pulled down by a planet. The next thing to realize is what are the units. So for mass, the units are going to be a scalar, or not the unit, sorry. Is it a scalar vector? For mass, it's going to be a scalar. Right? Mass only has a size. How much stuff in something is not related to a direction. So it's going to be a scalar. And then for weight, it's going to be a vector. And the reason weight's a vector is because it's a force of gravity. Right? Forces always have a direction. It could be left, it could be right, it could be up or down, but forces always have a direction, as well as a size, so weight's going to be a vector. Now the units for mass are kilograms, kg. So if you see 5 kg, that's 5 kilograms. And that's a measure of how much stuff is in something. Now for weight, that's measured a little bit differently. It's measured in newtons, right? Because it's a force. That's the standard unit for forces. Newtons would have an N, the symbol. And if you saw 5N, that would be 5 newtons. That would be telling you basically how much that object is pulled down. And in what direction. It's implied a direction. So again, if we saw like, I don't know, 5 newtons down, right, because you might see that because weight's going to be a vector. And the last idea in this table, this is important, is what changes based on other planets. So I'll draw this out again over here actually. So let's say you have a box and it's on Earth, E for Earth. So you have that box on Earth, it has some amount of stuff in it. Or it's made of some amount of stuff. And then let's say you brought that same box to Jupiter. And again, it's going to be made out of stuff there as well, the same stuff. So it doesn't matter where you bring it. Could be Earth, could be Jupiter, could be out in outer space. The mass is not going to change based on planets because if it's the same object, it doesn't matter where you put it specifically. But what is going to change is the weight. So weight is going to change, and that's going to depend on the planet. So on Earth, the force of gravity is going to be one value, and then on Jupiter, it's going to be another value completely. Because the force of gravity, the weight of something, is dependent on how much that planet is actually pulling down. And depending on the size and density of that planet, that force of gravity will change. So again, the same object could be on two different planets, Earth and Jupiter, could have the same amount of mass, but the weight could actually be different, and it will be different in this case. So that's important to keep in mind. Then the last idea really is that we can actually calculate weight and mass using this formula right here. So weight, right, which is equal, sometimes you'll see it's just written as Fg, which force of gravity is m times g. So m, you've seen that before, that's the mass. So again, it's equivalent to the mass times little g. And I'm going to talk about little g right here. So what little g is is the magnitude of acceleration of an object due to gravity. That sounds like a mouthful, but really what it is it's basically saying if you drop an object, how is that object going to accelerate? And basically how is its velocity going to change if you just let it go on a planet or something. So little g actually tells you what that is. On Earth, little g is going to be 9.8 meters per second squared. So if you drop something on Earth, it's going to accelerate downward at 9.8 meters per second squared. Now it's important to remember that little g is just the magnitude, so it just tells you the size of that acceleration. It does not tell you the direction. So you have 9.8 meters per second squared, that's g. So little g, 9.8 meters per second squared. That's how fast, or the rate at which it's accelerating. Technically, the acceleration is a negative, because acceleration itself includes a direction, a negative. Little g is just the magnitude. So again, that's important to keep in mind what little g is, how fast something's going to be accelerating. And on Earth, it's this value, it's 9.8 meters per second squared. On different planets, you're going to see it has different values. Okay, that's really all of the material, weight, mass, and the differences between them. So last thing, we're going to see a problem with this. So how would you see this kind of phrased in a problem? So see if you can solve this first. It's a fairly straightforward problem. There's a couple little tricks, but see if you can solve it first. Okay, I'll go over it. So what do we have? We have a rock, 5 kilograms on Earth, and it's asking what is its mass and weight on Neptune. So what is its mass and weight on a different planet, not Earth, Neptune. And it says the magnitude of Neptune's acceleration due to gravity is 13.3 meters per second squared. So let's check this. We have mass, 5 kilograms. We know g on Neptune. I'm just going to put a little n for Neptune. Right, because if you just normally see g, it's 9.8 meters per second squared. I'm going to just put a little notation on it so it's clear. It's going to be what? 13.3 meters per second squared. And we're looking for what is the mass on Neptune. I guess I'll put an n here. And what is the weight, or say force of gravity, same thing, weight on Neptune. So the first thing is the mass. So the mass is going to actually be the same. The mass is 5 kilograms because the mass remains the same on different planets. Because it's still the same amount of stuff. So mass remains the same. That's the explanation. 5 kilograms. And let's going to calculate the weight. So the weight, the way we calculate that is with m times little g. And we know the mass. We just said it's the same. And g is 13.3 meters per second squared. So 5 times 13.3, what do we have? It's going to be 66.5 newtons. So again, it's just a calculation. So actually that weight, if we think about it, it's going to actually be more than on Earth because little g is greater on Neptune. So that's the idea. Mass will stay the same. Weight is going to be different because little g is different on Neptune than it is on Earth. So for this, make sure you have this problem solution done. Make sure you have all the notes down. And that's it for now.